My mic okay? Yeah, okay, you're all responsive? Yeah. Excellent. Welcome all. Practical crypto attacks against web applications. So I had a slight concern just a little bit before as to whether I was going to be too basic. So hopefully I'm going to strike the balance between just confusing the hell out of you for an hour and boring the hell out of you for an hour. So let's see how that goes. For those of you who don't know me, if I talk too fast because I'm from New Zealand and therefore you can't understand what I'm saying, let me know and I'll slow down. Kiwis, we can talk fast sometimes. We just naturally do. So excellent. Overview. I am not a cryptographer. And actually, is there anybody who has crypto, like you call yourself a cryptographer in the audience? Good, because what I'm going to talk about today is, if you're not a cryptographer, this stuff is practical stuff to look at. So we're looking at, and there's three particular ones in particular that I'm looking at, which are repeatable patterns of things that you can look for, which are indicative of, and how you can actually look at kind of breaking those systems as well. And cryptography is wonderful, but if you use it badly, often you end up in a situation where it doesn't give you anywhere near the protection that you want. So using crypto does not equal security. Equally, crypto does not equal security. And the reason that I probably wanted to pitch this one in here and do this talk is because, I think there's probably certain people in here who do look for this kind of thing. In fact, I ran into Portswigger Daff just before, and he said that the latest version of Burp, is it in Burp Suite or Burp Pro or both? Or okay. Is going to have some bit flipping attacks, especially against things like cookies as well, which is exactly the kind of thing I'm going to talk about now. So it's something that you probably had to do manually up until this point. So we're going to look at the kind of stuff that we can do there. So perhaps this isn't something which has been well pen tested. If you've been around a long time, you probably have heard of, or you may well be a lot more expert in some of these things than I am. But the assumption here is that there's probably a few of you out here who are not probably figuring out that it's quite as easy to look for these kinds of things as it actually is. So, the basics. Confidentiality, integrity, and authenticity. So what are we trying to achieve? Inevitably, it's probably the first one, confidentiality. That's what we think of. We want it to be secret. But the other ones, and I've used authenticity instead of availability in this particular case just to fudge with those of you who know what the CIA actually is. But it's often kind of the actual integrity of the data and things like that is pretty damn important, but it's not something that we need to, it's not something that we often kind of consider. And it's often something that when you're doing something, when you're, say, a web developer, you're throwing something together, you're encrypting it, the way you do that can have some impacts on this kind of stuff as well. So, what are we actually going to look at today? So, because we just have 50 minutes, and because I am going to tempt the demons of fate and try and do live demos of this stuff, which may or may not lead to massive demo fail or not, we're going to look at three main kind of ones. So, we're going to look at ECB mode crypto, which even though you hear about the fact that it's bad, people still use. We're also going to look at padding oracles. And we're also going to have a brief kind of coverage on some of the random number generation stuff here. Now, all three of these scenarios are ones we find in pen tests. So, the question is, are you looking for them? And let's have a look at the kinds of things you should be looking for. So, if we're talking about the crypto, because we've got two different kind of symmetric crypto ones. For those of you who don't necessarily haven't dug into this in too much detail, we basically have a number of different ways that these things could work. The two ones that we're going to look at today are probably the two most common ones you come across, ECB and CBC. Of those, CBC is the one that you probably should be using. But the trick here is cryptography, encryption doesn't equal integrity. Can anyone tell me what happens if you take crypto, so you take ciphertext and you flip a bit and then you decrypt it? What happens? Yeah, you'll get a slight change in the clear text. Now, it's not predictable what that's going to be. but, equally, you may as well sit there and flip them just to see if you get anything interesting. So, I mean, used in isolation, these things don't provide any integrity. And a lot of the things that we're going to talk about, at least, especially for the first part of this talk, are directly related to that. So ECB is kind of like the default mode. We're looking at block encryption. So block encryption, who can tell me what kind of a common block size would be? What kind of block sizes are we talking about? 64-bit, 128-bit. So those are probably the two most common ones you'll come across. So 64-bit, very common for things like triple DES. AES, usually 128-bit. What does that mean? It means 8 bytes or 16 bytes. So if we're not quite familiar with kind of like thinking of bits versus bytes, we are talking like discrete blocks. What happens? ECB, you take the first block, you encrypt it. You get the next block, you encrypt it. Next block, you encrypt it. Why is that bad? Because actually, it's not bad because it's using the same key. What happens if the plaintext is the same? You get the same ciphertext. Yeah, so I mean, ECB mode has been known to be bad for as long as there has been ECB mode. Why it's not even there? So here's an example. Take a graphic, and although it hasn't turned out particularly well in this particular case, encrypt it with ECB mode. What do you get? Well, you don't hide the patterns for a start. It is encrypted, but there's a lot of information which is exposed there. However, we continue to see people using ECB mode because it is supported in all of the major crypto frameworks. So it's almost as if they should probably really just take it out. But it does have some, so people will continue to use it. So what kind of scenarios are we talking about? So, take something like this, cookie value, for example. Say we have an encrypted cookie value, and it has various kind of things that we have user IDs, roles, names, the kind of thing that you might end up sticking in a cookie on a legacy system or something like that. So let's assume that we've actually encrypted that. So we've taken this, we've done it on using a 64-bit one in this particular case. We have 8 bytes, and we've encrypted it. So that's fine. It looks secure. It's hex. It's secure, isn't it? Yeah. What happens if we actually swap things around? So I mean, we're not talking about anything rocket science in this particular case. But if we have an element of predictability about what is actually in these particular things, and there is a direct correlation in ECB mode between what block is what bit of data, we can just have fun and play with things. So in this particular case, we've swapped kind of block 7 into where block 2 is, and then when we have the decryption operation happens, we have something quite different. So in this particular case, this is a contrived example of this case, but we've gone from roll 3 to roll 39. What does that mean? Well, in the context of the application, who knows? But it's interesting that this kind of thing is not something that we're generally kind of looking for. So we have, a bit of differentiation there. So now we have, we'll see if this works. So this particular example is based on a live example that we did see at a client. So let me introduce a few bits and pieces. So first of all, let me introduce you to the stock trader application, which hopefully is still working. And it's probably also, yeah, turn that off. So as you can see, license copy. So let's go and have a look and see what we've got in here. So let me just maximize this because this is a relatively simple example. So this is an example application I'm just going to use for a couple of things. Now there's an interesting piece of functionality in this application, which is basically it's a self-registration functionality. And what happens in this particular functionality is we just register a user. So let me just put test. And what happens is, let me see, you're not going to actually see that unless we look at the, suffering from resolution a little bit here, is we end up with basically a single sign-on pass-off between two different systems. So in this particular scenario, we have a system which does enrollment, and it's basically doing a single sign-off pass-off to another system, which is authenticating. So this kind of scenario does come when you've kind of rolled your own single sign-on, or if you have perhaps a legacy system where you're logging somebody in, and then you're basically kicking them over to a new system, probably as part of kind of a rollover period. In this particular case, we have, the first thing is it's like, I'm always interested in anything which is hex, but it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm especially interested in anything which is divisible into blocks of 8s, because it's automatically a little bit suspicious. Now, in this particular case, we have a pure hex value. It could also be base 64'd. It could be encoded in a number of different ways as well. So it's something which is of interest. I'm also very interested in situations where we possibly have the ability to put something into something which is encrypted. So if we have the ability to force the application to encrypt something for us, and they observe the outputs. And that's the particular example in this case. So the example that we have in this case is this. So let me log out. Now, to skip several stages, there is an account called admin. And strangely enough, you can't create another account called admin. Because the way that the authentication for this particular application works, it is a login handover. But what kind of stuff could we do? Well, let's have a look and see what happens if we do stuff like this. So, and I'm just going to do a few of these, and we'll have a look and see what it looks like. I'm just going to call xadmin. xadmin. I'll do one more just so we have a look and see what we're seeing. xadmin. Let's have a look and see, where are we? Where's my bit gone? Too many windows. Okay, so let's have a look and see what we've been seeing. So there's the second one. So 09, there's another one, B7. Excellent. Okay, interesting. It's now got longer. Okay, so what's happened in this particular case is we're actually started another block. Okay, so this is interesting. So generally speaking, what we're going to do is we're going to continue adding x's in this particular case. And I'm going to skip a few steps because we actually end up doing about 9 of them or something other in this particular case. What's happened in this particular case? Well, whatever's in there, by putting the x's, is now spilled over into the next one. So we have, presumably, xxx a, and then, or maybe xxx a d m n m I n, and then the last block is actually the n. So let's just skip a couple of steps and show you kind of where we're going with this. So let me create 3 more. So that's how many? That's 1, 2, 3, 4, 5, 6, 7. There's 8. And we'll do one with 9 as well, just to get this complete. So let's go and have a look and see what kind of results we get with that kind of thing. So where's my pointer gone? Okay. So it was the last one. That one was when we just basically we'd made admin greater than 8 bytes. It was 9 bytes long. So if we go down and have a look at them, so that was 7, or maybe was it 6 X's? I think it was 7 X's, 8 X's, so, and 9 X's. Okay, so that's interesting. Now we have exactly the same thing. So if we're doing this kind of thing, up until now we probably don't know what that is, other than the fact it seems to be predictable, or seems to be contain some stuff that we've put in there. But now it's pretty clear that what's in that first kind of 16 bytes. What is that 352 2F2 whatever it is? Yeah, it's 8 X's, and that's it. So because we still have 8 X's on the front of it, so likely as not, and we see this because the first block is exactly the same. It's probably ECB mode. So what is, if we have a look at it, 6.3, what is 45A9, etc.? What is that? Admin. It's probably admin encrypted. And, just because we've got to prove these things. And this is when Justin hopes this actually works. Because even though you test these things the previous night, you're never 100% sure it does going to work on the day. So that's the value that we extracted, which logs us in as admin. So this is a very simple example, but this is based on a concrete example where we did exactly this. The only difference in the example that we actually exploited was this was a cookie. And the only other kind of bit was, instead of putting basically stuff on, in that particular case, instead of putting stuff on the front of the username, we're actually putting stuff in the middle of the username. And that was largely because of how they did their usernames and stuff like that. But it's literally, if you see pieces of data with that, you have to play with them and see what happens. So this particular one is a nice, easy example. But you occasionally will come across exactly that kind of thing. So, ECB mode, it is generally bad. So what about CBC mode? So ECB mode came out, and everyone said, oh, that's actually not a particularly good idea, because we could do block swapping. So what we're going to do is we're going to do cipher block chaining. So what we're going to do is we're actually going to XOR in effectively something to make the next block dependent on the previous one. So the way that it happens to be implemented in this particular case is, first of all, this is where you have an initialization vector. What's the initialization vector used for? And Vladimir, you've been answering lots of questions. Initialization vector, what's it used for? It's made to make it's used to make the first block not predictable, because we're not mixing in anything previously with the first block. So if the first block was always the same, it would be always the same. We'd end up with having some predictability about that. So the initialization vector kind of mixes some stuff in right to start with. And effectively what we're doing is we're XORing in the ciphertext from the previous operation with the plain text and then encrypting that. So effectively we're building a dependency. So this looks all really good. And I like these diagrams which have pretty boxes and XORs and arrows, and plain text goes here and ciphertext goes here. But, so we have XOR operations there, so that's what the arrows are there for. And it does what it's intended to do. It does mix in and kind of break a lot of those patterns and things like that. But implementation is a bitch. So the decryption operation is effectively exactly the reverse. So we end up with the initialization vector, ciphertext, decrypt, XOR, plain text. So we are doing the XOR operations in reverse in order to be able to do this. What's important about this is we're actually XORing in the ciphertext from the previous one. So it's just the implementation. And block swapping will result in corruption. So you can't swap them around, you'll end up with nonsense. Note, this doesn't mean that you won't be able to decrypt it. You'll be able to just arbitrarily stick whatever you like into an encryption algorithm, for the most part, and force it to decrypt. You'll just end up with nonsense. You're not going to end up with what you're looking for. But the way people implement systems based on these can have problems. And this is where the padding oracle is a particularly good example of this. So what is a padding oracle? It has nothing to do with Oracle. So we're not going to talk anything about databases. This is a kind of crypto issue. It's also a crypto issue which has been known about for a long time. I think the first kind of public paper on this was maybe 2002. A lot of you may have heard, because April last year I think it was, that a couple of chaps whose name Giuliano and I've completely Thai presented a paper at Black Hat Europe last year, kind of looking at practical attacks on JSF. September last year, this really kind of burst onto the scene because there was a major padding oracle exploit in .NET. So what are we actually talking about? Well, we're talking about bit flipping of ciphertext. So we have ciphertext and we have the relationships between blocks of ciphertext. So we can actually bit flip and just basically just start changing things to see what happens. But in this particular case, we're looking at a behavior of how the system is implemented, which, based on this behavior, we can get more information. And what it leads to is the ability to actually arbitrarily decrypt the data without knowing the key, without even knowing the algorithm, entirely based on the behavior of the system itself. So the first thing we have to talk about when we talk about padding oracles is what is padding. So when we're encrypting stuff, because we're encrypting blocks of 8, blocks of 16 data, if you don't have a block of 8 or block of 16, you need to pad it. So you need to stick something on there in order to have something to encrypt. And this is PKCS5 padding. Basically, if you have 3 bits of data, you need to pad it then with 5 more bits of data. In this particular case, you end up padding it with 5 lots of hex 5. If you have 6, you end up padding with 2 lots of 2. If you end up at 7, you end up padding with 1 of 1. And interestingly, if you actually do have 8, you'll end up padding it with 8 lots of 8. So this is a very standard padding behavior. It's not the only one you'll come across, but it's probably the most common one that you'll come across. And the reason that you do this is that so you can validate that you decrypted something correctly. Because if you decrypt something and it's correctly padded, then it was probably successful in the decryption operation. So this is one of the useful ways you can tell whether you've actually managed to successfully decrypt something or not. So PKCS5, and what are we talking about when we talk about oracles? Well, there is only 8 possible padding sequences you could have in the situation of having an 8-block algorithm. So first of all, that's interesting. So we know for sure what at least 1 byte of this data is going to be, or it could only be 8 things. And depending on what it was, we could know more of them. So that's interesting. That's interesting. And so what happens if we do kind of bit flip in CBC mode? So say, for example, in this particular case, we do flip, for example, the 6th kind of byte in this kind of situation. Well, we're going to end up with that kind of stuff affecting the plain text. But interestingly, it's also going to end up affecting the plain text of the next block. Okay, so that's interesting. So this is all kind of like about how it works. And based on how the decryption operation itself works, and this is especially how it commonly works in something like a web application, is we're probably going to end up with a number of errors if the decryption operation fails in some particular case. Even better if we know what those errors are. So the one that we're particularly interested in is, so invalid keys. Well, hopefully we're not going to get one of those. Is it an even block multiple? So those ones are only if you're kind of like feeding in invalid data. The one we're particularly interested in is an invalid padding exception. So how is that going to be useful to us? So this one is interesting because part of this is we need to be able to determine whether we have this error. So what happens commonly in something like a web application if you try and do something with data and it fails? Did you get a web application error? Maybe it even bubbles up an error message, an explicit error message, if you're lucky. But more to the point, you're likely to see a different behavior. You might get a 500 error where previously you were expecting a 200. So there's some observable behavior if we manage to cause one of these things to happen. So what are we talking about with a padding oracle attack? And this is where the oracle bit comes in. Because the oracle means that we have the application, the system as it's implemented, is telling us whether we have this or not. So effectively, the application as it's implemented is telling us that this situation does exist. So let's take the example. So we're going to flip the last byte of the ciphertext. So first of all, we're going to end up with rubbish plain text. We don't care. But, so we're going to call that one byte x. So byte x maps to byte y. So basically, it is XORed with the results of the next one. So it does affect the next operation. So what happens if the plain text isn't correctly padded? Well, this is the situation where we have it. So previous block, we changed that. Or actually, we just put it as a 1. It is going to affect and it be XORed. And at the end of the day, the plain text which comes out of the next block, if it's not validly padded, we're probably going to get an exception. So here's an example. We put in 0. So, so we put in 0, we get an exception. We put in 1, we get an exception. We put in 2, we don't get an exception. What does that tell us? What it tells us is if we stick a 2 into the ciphertext of the previous block, what must that value be if it's correctly padded? What? Sorry, was it? Yes, it must be a padding value. So it must be a valid padding value, of which there is only 8, and likely as not, we know exactly what that is. It must be 1. So we know what that value is. So we know if we stick a 2 in here, we get a 1 out here. So equally, we can continue that. And because we're talking about XOR, this means that we know other stuff as well. So more to the point, this is basically the intermediate kind of value, the one which comes out of the decryption and is then XORed with the ciphertext. It means we also know what that value is as well. So it means that we know effectively 3 different bits of information. So, I mean, effectively, that gives us the ability to kind of figure out what that unencrypted value is. It also gives us the ability, although we're not going to really talk too much detail about this, to actually be able to re-encrypt stuff with that block as well. So not only can we use this particular exploit to decrypt stuff, which is the simplest of the 2 examples, but we can also use this exploit to re-encrypt stuff. And we don't know the key. We don't even know what the algorithm is at this point. We're entirely looking at the behavior of the system and how it's implemented. So if our padding byte was 1, the byte that we stuck in, which is the 2, tells us effectively the intermediate byte must be such and such. I haven't actually figured out what that is. It's going to be something else. So we're just going to call that the intermediate one because it's effectively a value that we don't normally look at, but it's just interesting in that particular case. So let's just have a look at a practical example of this. Who's come across Padbuster? Padbuster, a few of you. So on the Gotham Digital Science website, we have a free tool which I'm going to demo. It is open source. It's reciprocal public license. Feel free to do whatever you want with it. Tool which exploits exactly this stuff as well. So let's have a look at doing that. So I'm going to do this against this particular application here. So as I mentioned, there's a padding oracle exploit or a padding oracle problem with .NET as of kind of September 2010 last year. So it was patched. So the version that the version I'm showing in this particular case is not patched. But I'm just going to demo it in this particular case. So there's a couple of bits and pieces in the .NET framework which are susceptible to padding oracles. Can anyone got any ideas? Can you tell me what they are? You guys are very communicative today. Okay, view states. So view states are a good one. But the one I'm going to particularly look at this case is resource handlers. So resource handlers, .NET 3.5, .NET 4, Ajax apps are particularly interesting. So there's two of them by default that you would normally come across. One's called the web resource handler, and the other one's called the script resource handler. Now, if you have a look into more detail about the padding Oracle attacks, you could actually use the script resource handler to do handy things like download the web.config off the site, which is kind of cool. You kind of just pointing it at something, decrypting it, re-encrypting it, and saying, give me the web.config, and it would. Now, unfortunately, I couldn't get that working, largely because this application here is not an Ajax application, even though it is a .NET 3.5 one. So what I'm going to do is I'm just going to show you an example of decrypting something rather through the web resource handler. So what the hell am I talking about when I talk about web resource handlers? So let me have a look at the target thing. We would have come across some of these. I'll break this down. We're talking about this thing. So what the hell is that? Effectively what it is it is a request which returns a script, effectively. So this bit of data is a script, or it's a pointer to a script. And in fact, it actually is a file name. In this particular case, it's interesting because with the web resource handler, you can actually download any JavaScript files which are inside an assembly DLL in .NET. The script resource handler is more interesting because you can actually pull down any file on the box. So unfortunately, we can't demonstrate that one in this particular case. So, and let me demo Padbuster. So hopefully this works. So it's worth pointing out at this point that Padbuster is not a specific tool for this particular issue. It's written by a colleague of mine, Brian, in New York. It is a general tool for all types of padding oracles. So it was actually originally written for exploiting JSF server faces view states. But it works quite handily with the .NET example as well. So main things we're looking at, we need to provide a URL, we need to provide an encrypted sample of data, and we need to specify a block size. So let's do that. So I'm just going to grab one of these. Help if I could spell. And when we're talking about encrypted sample, effectively it just needs you to tell it what the bit is that it needs to play with. So it's going to be that one. So 2J8EU51 blah blah blah. In this particular case, if I remember correctly, it needs to be 16. Is the block size? Where the hell's my pointer gone? And there's a couple other things we need to specify in this particular case. These are .NET specific ones, which are effectively telling it what kind of format the data is in. And so this particular case, encoding is .NET URL token, which is a particularly weird version of encoding. So .NET has its own particular one. And no IV means there's one of these, the IV is not included in this block. It's just a particular option for .NET. So let's see if this works. Okay. So what has it done? It has gone through and it has flipped effectively the last block of that to all 256 values, and it's just seen what happened. Now, what happens in a web application is going to be different depending on the application. You could see 200s, 302s, 500s, but more importantly, we have one which is grossly different to the other ones. So effectively, we're looking for the error condition at this point, so we can then effectively tell which ones are accurate and which ones not. So it's handily pointed this out that we should probably select 2 at this point. And what it's going to do is it's just going to go through the process of decrypting that piece of information. Now, I'll warn you now that the output of this is not very exciting. What's actually in here is not very interesting. But it is purely just to demonstrate kind of the output of this kind of thing. Yep, so the decrypted value is that, which is not very exciting. So effectively what it is a reference to S. So the way that this particular piece of data works is S is a particular type of resource, which in this particular case is an embedded assembly resource. And then you have piping, which are basically separators. And the resource is the web UI validation.js, which is a standard kind of Ajax-y kind of .NET thing. But more to the point, we still don't know what this key is, and we've just decrypted it. So I'll point out at this point that we're just having a chat with the guys from Defensive Security. Padbuster probably will be on the next version of Backtrack. But in the meantime, feel free to pull it down just off our website, gdssecurity.com. It's sitting there in the tools thing as well. So that's a nice little simple example. Also, if you have a look on our blog, there's some good examples of pulling down web.configs if you're particularly interested in how that works. Unfortunately, I couldn't get that demo working for this, as noted. So, both of the things that we've been talking about so far are purely because we have a situation where we have encryption things where we have the ability to change stuff. So we have the ability to change the ciphertext for the most part, swap things around, and it still works. So in these particular cases, largely because it hasn't been signed. So it might be worth looking at options for signing if you were trying to fix one of these things. So there's various types of ones. HMAX is one of them. But have a look into that. Interestingly, the .NET issue that we just looked at is signed. It's just signed. The signature is not checked until after you've decrypted it. So we're actually forcing the error before it actually checks the signature. So in this particular case, although at first pass the design looked good, because of where they were actually checking the signature, it was actually after the decryption operation as opposed to before. So we had that particular one as well. So other things which are vulnerable to this is the forms authentication cookie as well. That's a good one. So if you have an ASP.NET app, which has forms authentication cookies, that's another one which is susceptible to this too. JSF, view states, also susceptible to this. I don't think the JSF stuff's been fixed. Does anyone have any better? Yeah, I'm pretty sure the JSF is still vulnerable to this day. Although .NET has patched. Although I'm not 100% sure. I think it was put as an important patch, which means in some cases it may not have been automatically picked up. So it's worth checking to make sure you're not susceptible to this. And last but not least, because don't want to run over time, I'm going to talk about just and I don't have a demo for this particular one because unfortunately it's a little, if you're talking about random number generators, it's kind of like you need to run it half a dozen times to like have any chance of it actually working. But these kind of situations are good examples. How random is random? So you'd be surprised how often we come across situations where people are using normal pseudo-random number generators, and kind of where do those numbers come from? So typically, we may have problems with non-random seed values, or we may have kind of deterministic ones where we can actually predict or see what those things are as well. And it's surprising how often you see situations like this. So we have one series, two series. Effectively, what we're doing is we're just like creating a random number generator and just outputting stuff. Runs one after each other. And unsurprisingly, if it does, it outputs the same thing. Why is that? So in this particular case, that was .NET code. In this particular case, we didn't even supply a seed. Plus, we're using a crappy random number generator in the first place, and it seeds it off the clock. Okay, so if you're running a random number generator and you're seeding it off the clock, how predictable is it to be able to figure out what the clock on your server is? It's not that hard, is it? You can probably make an educated guess as to what the clock's going to be, especially if it's a Unix box and it's probably running GMT. If you've probably got a very limited kind of time frame as to what we're looking at in those cases. And you end up with like code like this, and this is based off an example we actually did see, where we have basically a random number generator for resetting a password. So you've requested a password reset, and it's doing it in a pretty crappy way from a security point of view. And what's it doing is it's emailing you out your new password. So that's fine. But can anyone tell me what the big problem in this particular case is? Well, there's no seed. Well, yeah, there's no seed, and it's a random number. What happens if you hit this like at the same time or close enough? What happens if I just send a lot of requests? Yeah, you're going to end up with the same password. And unsurprisingly, that's exactly what happens. And whoopsie daisy, what the hell happened there? Okay. Unsurprisingly, it is possible and it is reproducible in practice. Now, if you're doing something over the internet, needless to say, you're going to have an element of luck to get things turning up at pretty much the same time. But through a brute force approach, you can end up with situations like this. So there was an experiment, I've lost the reference to the actual paper that they did, but they were actually looking at a site which had password resets implemented in exactly the same way that we were looking at. And they found out that if they basically just sent lots and lots of password reset requests pretty much at the same time, they could end up with, and they could force situations where they had the same password sent to them as well. So in this particular case, if you have the ability to kind of like arbitrarily reset people's passwords, and you can reset yours at the same time, you have an element of predictability as to what that person's password is going to be. So it's something which is interesting and something to have a look at. And we were talking about .NET. You know, is Java any better? And that looks pretty random, doesn't it? Maybe if we do a two-dimensional plot, you know, it looks pretty random. Maybe not so. So Java has exactly the same kind of problems, although its default random number generator is a little bit better. It has much of the same kind of problems. So, to summarize, implementing cryptography is hard. And a lot of the situations that we just talked about are usage. So none of the stuff we've just looked at has anything to do with how strong the crypto we're actually using is. In the padding Oracle one, we don't even know what the algorithm is, let alone what options they're using. We don't care. It's all based on usage. So when you are implementing things, and more to the point when you're looking at other things that other people have implemented, and you're looking at that from a security point of view as well, you need to make sure that you give those things an element of rigor around kind of how it's designed, how it's implemented, and things like that. And when in doubt, ask an expert, which, by the way, I'm not a crypto expert. But hopefully, you know, within your organization or, you know, within one of the people that you rely on or something like that, you have somebody who can actually take that kind of look at something that you're designing. Because crypto is hard.